Okay, solving absolute value equations and inequalities. We learned last time what it meant to be an absolute value. Okay, the absolute value of 3 and the absolute value of -3 are both 3 because each of them are 3 units away from 0. So anytime we have those absolute value bars around something, that represents the distance that that value is away from 0. Okay. Again, as I mentioned, we're going to start solving equations that have those absolute value symbols in there. Let's first observe one of these functions on a graph and then see what it means when we turn that function into an equation. And then we'll relate this idea to solving algebraically instead of using a graph all the time. So if we look at the the equation, absolute value of x plus 2 equals 5, let's recall what it meant for that function as far as its transformation. Okay. Anytime I have a number inside the parenthesis set, or inside the absolute value rather, okay, that moves the vertex of that absolute value somewhere. Okay, in this case, plus 2 on the inside told us that we are supposed to go to the left 2 from the original parent function vertex of 0, 0. So my new vertex is 2 units to the left of the origin. Okay, and the shape of this function still remains the same. So in both directions, I'm going up 1 and over 1. I want to make sure my graph looks exact here. Okay, so that's my positive sloping side, and here is my I call it negative sloping side. Okay, it's not really a slope, but it kind of acts like a slope. Okay, now that I have that graph, okay, I want to see where those where that graph has an output of 5. Okay, I'm setting this function equal to 5. That tells me that my output is 5. I need to figure out what input values give me an output of 5. Remember, outputs are y values, inputs are x values. So if my output is 5, I can imagine a line right at the output of 5. Okay, and I want to see where that imaginary line crosses my absolute value. Okay, so if I look closely, okay, it crosses here, which is an x value of 3, and it crosses right here, which is an x value of -7. And those are my two solutions. Now, as you could see when I was doing the example, it was tough to find exactly where those 2 points are, especially if they're not whole numbers. So we want to see if there's a better way to find these solutions without having to graph all the time. Okay. And here's our first example that we're going to do together. Okay. Every time we have an equation that has an absolute value symbol, there are 2 steps. We're first going to get that absolute value symbol by itself. That's what isolate means. We're going to get it alone on one side of the equal sign. After that, in order for us to get our 2 solutions, we need to set up 2 problems. One for the negative sloping side, like we talked about on the graph, and one for the positive sloping side of that absolute value function. Okay, so I've got the function absolute value of 5x minus 10 plus 5 equals 50. First step is to get the absolute value symbol by itself. So I'm going to subtract 5 from both sides. I now have the absolute value of 5x minus 10 equals 45. So my next step, after I have isolated my absolute value symbol, is to set the positive portion equal to 45. I'm going to set up a second equation where I'm going to have that same value, 5x minus 10, equal to 45, but I'm going to account for the negative sloping side. I'm going to solve both of these equations for x. So for my first equation, let's add 10 to both sides. So I have 5x equals 55, and divide by 5 on both sides. So my first solution, x equals 11. That's on the positive sloping side. For the negative sloping side, let's just circle that answer. For the negative sloping side, I am going to distribute my negative sign. So I get negative 5x plus 10 equals 45. I'm going to do the same thing, solve for x. Subtract 10 on both sides. Negative 5x equals 35. Divide by negative 5, and x equals negative 7. Okay, just like that graphing example, if I were to graph the absolute value in this problem, okay, where it is set equal to 50, the outputs would be 11 and negative 7. Now I know that that's a little bit confusing, so I'll do another example just to get this solidified, get this idea solidified. So our 2 steps. Get the absolute value symbol by itself on one side of the equal sign. The good thing is on the left, I don't have anything else outside that equal sign. Sorry, absolute value symbol. There's nothing else outside the absolute value symbol. So I get to skip step number 1. Step number 2 says, set the positive portion equal to the output, and so we got a second equation, set a negative portion equal to that same output. I have to set up both of these equations every time, okay? So let's review. I took out what was inside the absolute value symbol, 2x plus 12, and I set it equal to the output. I took that same absolute value, set up a new equation, and all I did different was put a negative sign in front of it. That's how you'll set up your 2 equations every time. Okay, that will give us our 2 solutions. Okay, so let's solve both of these for x. Subtract, oh, I lied. We have some terms to move over, so I'm not going to move that constant. I'm going to move my variable to combine it with that 4x. So I have 12 equals 4x minus 2x is 2x. And when I divide by 2, I get x equals 6. Okay. Let's distribute the negative sign. So I got negative 2x minus 12 equals 4x. Same idea, combine my x's. Negative 12 equals 6x. And divide by 6. So x equals negative 2. Now, there's one extra step here. It says check for extraneous solutions. Okay. What I have to do if it asks me to check for extraneous solutions is plug this x value back into the function and make sure that it gives us a true statement. Here's what I mean. I'll change colors for this. I'm going to plug this x value into my original equation and make sure that that equation is true. So the absolute value of 2 times 6 plus 12 has to equal 4 times 6. Well, on the left side, absolute value of 2 times 6 is 12, plus 12 has to equal 4 times 6, which is 24. Okay, well, 12 plus 12 is 24, so on the left I have absolute value of 24 has to equal 24. Okay, ask yourself, is that true? What is the absolute value of 24? Is it 24 units away from 0? Yes, it is. So I know that this is a good solution. Okay, let's check -2. Plug it in that same spot in the equation. So I've got absolute value of 2 times -2 plus 12, and the absolute value equals 4 times -2. Okay, absolute value, 2 times -2 is -4, plus 12 equals 4 times -2 is -8. Okay, absolute value, -4 plus 12 gives me 8, equals -8. The absolute value of 8 is 8. Does that equal -8? No, it does not. So this is what we call an extraneous solution. My only answer here is x equals 6. Okay, -2 makes the equation untrue. So that does it for our equations. We have an equal sign there. But remember, we can solve expressions that have an inequality symbol. We're going to see how this changes our approach to solving. Let's graph the function f of x equals absolute value of x minus 2. Let's see what this looks like. Okay. That minus 2 on the inside tells me that the vertex moves 2 to the right. From there, it remains the same as the parent function. Okay, so there's my positive sloping side. Trying to be exact as I can. And there's the negative sloping side. Okay, just like we had before, okay, if this was an equals sign, okay, I would have two solutions where those two things crossed. However, this is an inequality. We're talking about everything that is strictly less than, okay, strictly less than 4. Okay, so I'm talking about all the values underneath that line. Okay, all of those ordered pairs that fall on that portion of the graph count as solutions, excluding the end points, because it is a strict inequality. There's no line underneath there. Okay, that's an annoying way to find the answers. We want to find those answers algebraically. Got one more example before we do that. Okay, this time we've got a greater than or equal to symbol there. Again, let's go ahead and see what this graph looks like. Okay, my transformation there is +1, so that moves my vertex 1 to the left. Okay, and I've still got my shape of the parent function, up 1 over 1 in both directions. And it's everything greater than or equal to 3. Well, my portions of the graph that are greater or equal, so I've got my two equal points, everything greater is this portion, but I have another portion. Okay, so this time, instead of having these values underneath here, which don't count anymore, I have two separate portions of the graph that represent the solution. Okay, we're going to learn how to solve both of them, both types, and state the solution algebraically instead of doing these ugly graphs. So here's our first kind of concrete example of solving an absolute value inequality. Okay, we're going to do it the exact same way that we solved an equation. Okay, I'm going to set the positive portion equal to or less than 13, and I'm going to set a negative portion less than 13 and solve both. We'll sketch the solution and write our solution as an interval at the end. So solve for x. Subtract 5. 13 minus 5 is 8. And to solve for x, I divide by 4. So x is less than 2. That's the first part of my interval of solutions. The next part, solve for x again. Negative 4x minus 5 is less than 13. Add 5 to both sides. Negative 4x is less than 18. Let's go ahead and solve for x by division. That should put a little red flag in our head. I've got an inequality and I divided by a negative. So that is going to flip my sign. 4 doesn't go into 18 evenly, but it is a reducible fraction. Got a negative sign there. They're both even, divisible by 2. So I've got 9 over 2. I have my answer, but I want to express it a little bit cleaner. So I can sketch my solutions on a number line. Okay, the smallest value is always going to go on the left. We've got negative 9 halves here. Let's throw 0 in there just to give us an idea of where we're at. And I've got 2. Okay, my first part is all x's that are less than 2. Strict inequality, so it cannot equal to. We've got an open hole. And less is everything to the left. And we'll kind of stop for a second. Okay, because we want to make sure that we include all x's that are greater than, so strictly greater than, negative 9 halves. Okay, greater is going to the right. So if I shade these both at the same time, they're going to shade together. So I've got a solid line between those two values that represents my solution. Let's write that in interval notation. Smallest value to biggest value. They're both exclusive. We cannot equal those, so they are going to be our parentheses or our rounded brackets. Okay, so we'll sketch our solutions and we are going to write as an interval. Okay, here's our last example. The absolute value of x plus 4 is greater than or equal to 6. Let's go ahead and set up our two equations. X plus 4 is greater than or equal to 6. And the negative portion, negative times x plus 4 is greater than or equal to 6. And we do that every time. Okay, it's accounting for both portions of our absolute value. Now I can solve for x and write my answer. Subtract 4, so x is greater than or equal to 2. Distribute the negative. Negative x minus 4 is greater than or equal to 6. Add 4. Negative x is greater than or equal to 10. Let's get rid of that negative sign. So x is now, flip the sign, less than or equal to negative 10. I can sketch. Okay, your sketch is going to look a little bit different. My smallest value is negative 10. Let's get 0 on there, and my largest is 2. I can equal to, and it's everything greater, so I'm going to shade to the right. That is the greater portion of the graph. My smallest value is -10, and I can equal -10. And I've got everything less than or equal to -10, which tells me to go to the left. Okay, so these two portions are going to point away from each other, which is completely legal. Let's write this as an interval. Okay, in our last example, the smallest possible solution was -9/2. Okay, in this case, I can go forever to the left. So my smallest value is -infinity. The end of that first interval is -10. It is inclusive, so I square off my bracket. I have two portions of this interval, so I'm going to have a union here. It picks back up at 2, and it includes 2. And the largest value on the entire interval is infinity. I can't touch infinity, so I'm going to round that bracket. Okay, let's review. I can solve equations and inequalities involving absolute values. Our first step is to isolate the absolute value. After that absolute value is alone, I set that absolute value and its negative portion equal to the output. From there, I can solve for my possible solutions.